Hello everyone. In the last lecture, we had talked about set builder form of a set, and we had also seen operations on sets. We talked about union of sets, we had talked about difference of sets, and we had talked about intersection of sets. In the lecture today, I'm gonna introduce the notion of intervals first, and then we are gonna see some problems based on operations of sets. So let's define the intervals then. Suppose you are given two real numbers a and b with a less than b. Then we define four type of intervals. This is the first one called as the open interval. So this is the open interval a to b. This is the closed interval a to b. And these two are called the semi-open intervals. Now let's talk about the open interval a to b. I'll try to give an example to illustrate the same. So for example, let me take an open interval. Okay. Definition of the open interval AB is we are collecting all those x such that x is a real number and values of x are varying from a to b and not including the endpoints. X is strictly greater than a, x is strictly less than b. So for example, I can consider this open interval 2 to 3. By the definition of intervals, if I'm talking about the open interval 2 to 3, that would be collection of all those x such that x is a real number and x is strictly greater than 2 and x is strictly less than 3. So it can be anything between 2 and 3. For example, it can be 2.1 or it can be 2.2 and so on. On the number line, this is represented by marking 2 and 3 here. We are not including 2, we are not including 3. So to indicate the fact that these endpoints are not supposed to be included, we make a circle around them. So 2 is not included, 3 is not included. Everything in between is supposed to be included. To represent the same, we shade the middle portion. To denote the fact that everything between 2 and 3 is supposed to be included, you shade the middle portion. And that's what open interval a to b is. The open interval 2 to 3 in this case is the collection of all the numbers between 2 and 3. In a similar manner, we'll talk about the closed interval this time. By definition, closed interval AB is the collection of all those real numbers such that x is greater than or equal to a, but x is less than or equal to b. In this particular case, a is being included, b is being included as well. This equality is there, so that tells us a is gonna be included, b is gonna be included as well. Now, so we are gonna include the 2 this time, we are gonna include the 3 this time. We are talking about the closed interval 2 to 3. X is supposed to be greater than or equal to 2, x is supposed to be less than or equal to 3. To denote the fact that the endpoints are included, this time we are not going to draw a circle, we'll just mark the point, that's all. Coming to the semi-open intervals, here it indicates the fact that A is supposed to be included, not the B. Here A is not to be included, but B is supposed to be included. So let's consider that. This time we'll include the 2. So putting an equals to mark here. And then in the other case, we're not going to include the 2. So 3 is supposed to be included here. So it would be this semi-open interval. 3 is to be included. So let's mark it on the number line now. We are including the 2, not the 3. So to denote the fact that 2 is to be included, you mark the point 2. 3 is not to be included, so we'll keep the circle with on the 3. This circle is going to remain as it is. And for the fourth case, it's a semi-open interval 2 to 3. 2 is not to be included, 3 is supposed to be included. So 2 is not included here, already marked, but we are supposed to include the 3 this time. So we'll mark the 3. So that's how the intervals are working here. Let's talk about now the operations. We'll talk about some operations which are using the intervals. First question here I have is collection of all those real numbers such that 2x minus 1 is strictly greater than 1 less than equal to 4. That's the set A defined to us. The set B has been defined as we are collecting all those real numbers such that 2x plus 1 is greater than equal to 1 but less than equal to 4. So let me consider the set A first. I'll try to see what the set A looks like. In the set A, 2x minus 1 is strictly greater than 1 but less than equal to 4. What I'm trying to do is I'm trying to solve for x here. To do that, first what I'll do is I'll add 1 throughout this inequality. So on the leftmost side, I will have 2. 2x minus 1, when I add 1, it will becomes 2x. And similarly, on the right side, you will have 5. And this time you divide by 2. And when you divide by 2, you will have x is greater than 1, but less than equal to 5 by 2. So this is what our x is. This thing tells me that values of x are coming from this semi-open interval 1 to 5 by 2. 1 is not to be included, but 5 by 2 is included. So the set A is gonna be 1 comma 5 by 2 here. That's set A I have. Similarly, we do the work for the set B. For the set B, again I'll consider the inequality here. The inequality given to us is 2x plus 1 is greater than equal to 1, but it is less than equal to 4. Again, I'll try to solve for the x, for which I'll subtract 1 throughout first. So that would give me a 0 on the leftmost side, 2x here, less than equal to 5, 3. 4 minus 1 gives me a 3 here. And then again I'll divide by 2. That will give me 0 here, x here, and 3 by 2. So this tells me the values of x are coming from the closed interval 0, comma 3 by 2. To visualize things better, let's just draw the number lines. The set A here is semi-open interval 1 to 5 by 2. So 1 is not to be included, so you draw a circle around it. 5 by 2 is to be included, so we'll mark the point. And then everything in between is supposed to be included. So this is what the set A would be. As for the set B, I will have, so this is the set A we have. The set B here is 0, comma 3 by 2. So we are going to talk about the A intersection B then. I have marked the A here. Let me draw the set for B also. The number line will have 0 to 3 by 2 we are considering. 0 would be on the left of 1. 3 by 2 would be somewhere in the middle of 1 and 5 by 2. So these are the 2 points we have. Both endpoints are included. So we are going to mark these 2 points and then everything in between. That's the set B we have. So the first one was the set A. The second one is the set B. Question is, what is the common portion? A intersection B. B means we are looking for the common portion. Now common portion would be then from 1 up to this 3 by 2. From 1 up to 3 by 2 would be the common portion. 1 is not going to be included. 3 by 2 is to be included. So A intersection B, the common portion is 1. 1 is not included because 1 is not there in A. So 1 cannot be common to both. And then 3 by 2. 3 by 2 is to be included because 3 by 2 is there in B and at the same time it is there in A as well. So A intersection B is going to be 1 comma 3 by 2. So that's the set A intersection B we have then. So that's the answer we have then. A intersection B is going to be the semi-open interval 1 comma 3 by 2. And that's the option A with us. So first what I did is I just tried to see what A looks like. I solved this inequality, which gave me that A is the semi-open interval 1 comma 5 by 2. Then I solved the second inequality here, which gave me values of x are varying from 0 to 3 by 2, which tells me the set B is the closed interval 0 to 3 by 2. I marked the A on the number line. I marked the B on the number line. Question was asking you what is the A intersection B. Intersection B means we are looking for the common portion. Common portion is this portion from 1 up to 3 by 2. 1 is not included because 1 is not there in A. 3 by 2 is included because 3 by 2 is there in both of them. And that's how we have the answer A intersection B. Let's move on to the next question. In the next question, we have two sets are given to us. A is here and then B is given to us. B is clearly given, B is clear, it's minus 3, 5. It's a semi-open interval, minus 3, 5. We just need to work out the things for A here. B is clear, B is gonna be this interval. Now coming to the set A then, in the set A I have, question says A has all those real numbers m such that both the roots of this equation are supposed to be real. So I have been given a quadratic equation and question says what values of m should we take so that both the roots are real. Now given a quadratic equation, we know that when the roots are real, discriminant is supposed to be greater than or equal to 0. This is the quadratic equation we have, and I want the real roots for this equation. The equation has real roots, so the discriminant is supposed to be greater than or equal to 0, where this discriminant d is equal to b square. B square in this case is m plus 1 square minus 4 into a into c, which is m plus 4 here. Now when you simplify the d, you're going to have m square minus 2m minus 15 greater than or equal to 0, which can be factored as m minus 5 into m plus 3 greater than or equal to 0. Now you need to choose all those m which will satisfy this inequality. I'm looking for all those values of m for which m minus 5 into m plus 3 is going to be greater than or equal to 0. This you can figure out by taking the number line then again. Figure out where this thing becomes 0. Figure out where this thing becomes 0. Mark it here. M minus 5 becomes 0 at the point 5. M plus 3 becomes 0 at the point minus 3. The next thing we'll do is we'll see in this interval what happens to these two quantities. One way is anything which is greater than 5 will give you a positive number here, will give you a positive number here, and therefore the product would be positive. So any number on the right side here will give me positive values here. Or the other way, you can just take any random number here. Let me take 6 for example. 6 minus 5 becomes 1. 6 plus 3 becomes 9. Product would be 9, which is greater than or equal to 0. Meaning any number you take on this side, the product is always going to be positive. Now see what happens when you take 5 also. Anything on the right side of 5, I will have a positive number. If I do take 5 though, it becomes 0, which is allowed because there is an equals to sign here. So I can also include the 5. That's one thing we are done. Second interval I'm gonna consider is this one, minus 3 to 5. Then again you can choose a random number in between minus 3 and 5. Let's say we'll take 0. 0 minus 5 is negative. 0 plus 3 is positive. Product of negative and positive is a negative number. So I am having a negative number in minus 3 to 5. Coming to this interval now. Then again, I'll leave it for you to verify that it is actually going to be a positive. And for the point minus 3, when I put the minus 3 here, the left side becomes 0, which is allowed. So 0 can also be taken. Now what we have done here is we were having some inequality. We tried to figure out what all possible values of m will give me the positive product. I observed the product is positive here, the product is positive here, and I am also allowed to take minus 3 and 5 because there is an equals to sign here. So the values of m we are looking at are minus infinity to minus 3. Minus 3 is allowed and therefore the closed part. Union 5 to infinity. 5 is included as well because then again there is a 0 and 0 is allowed. So this is what values of m are. These are the possible values of m, and therefore we have found out what the A looks like. A is the set minus infinity to minus 3 union 5 to infinity. That's the set A we have here. Let me mark it on the number line. So I'll shade the part this time. So it's this thing here and then this part here. The endpoints were allowed, so I'll mark them here 3, mark them here 5. That's the set A for you. As for the set B, it's already given what B is. B is the semi-open interval minus 3 to 5. So this is what we have. Let's mark it here on the number line, this as well. For the set B, I will have everything is from minus 3 to 5. So minus 3 is included, 5 is not. So minus 3 is included, so you can mark the minus 3. 5 is not supposed to be included, so we'll make a circle around it here. Now, question asks you amongst the options, which is not true. So we'll take a look. Let's talk about the first option here. A minus B is what I'm supposed to look at. Now, definition of A minus B as we know is we are taking all those x elements of A which are not in B. So I want to find elements of A which are not there in B. That's what A minus B is. So let's look at the elements of A. Elements of A are from here to here and then from here to here. So I'm looking for those elements of A which are not in B. Let's look at this portion of A. If I consider this 5, it's not there in B, so we are good with the 5. Anything on the right side of 5 is not there in B either, which means this whole portion from 5 up to infinity is going to be there in A minus B. So A minus B will have 5 to infinity, that's one thing it has. Union, now consider the left side of A. We want to take only those elements of A which are not in B. If I start at this minus 3, it's there in B also. So I cannot take this minus 3. Anything on the right side of this minus 3 is not here. That I can take. I cannot take this endpoint because they are both common in B and A. Anything to the left of minus 3 doesn't cause any issues. So what we are having is numbers are coming from minus infinity to minus 3. Now this 3 is not supposed to be included and therefore an open interval. Now let's look at the option A. Option A says A minus B is equal to minus infinity minus 3, which is what we have. Union open interval 5 to infinity. But I have a closed part here. 5 is allowed. So option A is not right. So the correct option we are looking at is option A. I'll just talk about A intersection B and then I'll leave the other two for you to verify yourself that they are actually correct. Let's talk about the option B. Intersection means we are looking for common portion. If I look at 3, 3 is there in both of them. Nothing which is here is here. So 3 is fine. 5 is not there either. So the only common point that I see between the two of them is the minus 3 alone, nothing else. So intersection is going to be minus 3. That is why this statement was correct. We are looking for statements which are not correct. This is correct. I'll just leave the other two for you to verify yourself. So correct answer we are looking at is A minus B, and that's gonna be this. For the next question, we have this. Given the set A has all those real numbers such that modulus of x plus 1 is less than 2, and B is the collection of all those real numbers which has modulus of x minus 1 greater than equal to 2. Then again the question says which of the following statements are not correct. So we are supposed to look for statements amongst these which are not correct. Then again we'll try to see what A looks like, we'll try to see what B looks like, and then we'll draw conclusions from there, which means I need to solve these inequalities. So I'll just mention some results related to modulus function first, and then we'll talk about the result question here. So one of the result is modulus of x, if it is less than equal to a, then the values of x are varying from minus a to a, endpoints included. If it's a strict inequality, then what you have is minus a to a, and the endpoints are not included this time. That's one thing we have when things are less than equal to a or less than a. The other case is modulus of x greater than equal to a. In this case, what you have is either x itself is greater than a or equal to a, or the values of x are smaller than equal to minus a. And the second case, modulus of x is less than strictly greater than a, that would be x is either greater than a or the values of x are less than minus a. So I'll use these results to solve the inequalities that have been given to me first. We'll try to see what A looks like, we'll try to see what B looks like, and then we'll talk about the options given to us. For the set A, what I have is collection of all those real numbers such that modulus of x plus 1 is strictly less than 2. So let's solve this inequality here. Modulus of x plus 1 is strictly less than 2. That's this case we are looking at, which tells me I'm going to have values of x plus 1 are varying from minus 2 to 2. Instead of a, I have 2. Instead of x, I have x plus 1. So instead of x here, I will have an x plus 1 here. A is 2 for us. Now adding minus 1 on all side, I will have minus 3 here, an x here, and a 1 here. So this is what we have. This is an interval, the open interval minus 3 to 1. So the set A is actually equal to minus 3 to 1. That's the set A we have. Now let's go to the set B this time. Set B has collection of all those real numbers for which modulus of x minus 1 is greater than equal to 2. So again, I'll try to solve the inequality first, and then we'll take it from there. I have modulus of x minus 1 greater than equal to 2, and that's this case we are looking at. Modulus of x is greater than equal to a. So instead of x, I have x minus 1. Instead of x, I have x minus 1. Instead of a, I have 2. So it is going to be same as x minus 1 being greater than equal to 2, or x minus 1 is going to be less than equal to minus 2. First thing gives us x is greater than equal to 3. Second one gives us x is less than equal to minus 1, which tells you either the values of x are coming from minus infinity to minus 1, or they are coming from the interval 3 to infinity. And that's what your set B is gonna be. B is equal to minus infinity to minus 1 union 3 to infinity. Now we'll talk about the options that we have. But before that, let me mark these A and B on the number line first. So this is the A we have, and let me mark the B here. For A, I have minus 3 to 1, the values. For the set B, I have minus infinity to minus 1 first. Minus 1, let me mark the minus 1 here, and then 3 to infinity. So let me put the 3 here. The shaded portion for A would be from minus 3 to 1. Endpoints are not supposed to be included. It's an open interval. So we'll circle the 1 here. We'll circle the minus 3 here. Coming to the set B has elements from minus infinity to minus 1. So we'll shade the minus infinity to minus 1 portion first here. Minus 1 is allowed, so we'll mark it. And then the other one we have is 3 to infinity. 3 is also allowed, so this is also good. So this is a shaded portion. Now let's talk about the option this time. In the first one, I am supposed to consider A minus B. For the first part, I'm supposed to consider A minus B. Just like in the last one, we had A minus B simply denotes elements of A are to be taken and not the B. Same thing here also. I'm looking for elements of those elements which are in A but not there in B. So if I look at the portion from here up to minus 1, let's suppose minus 1 is here. From minus 3 up to minus 1, things are common between A and B. From minus 3 to minus 1, things are common, and I am not allowed to take the common portion because we are taking the difference. Let me mark the minus 1 here. Yeah, minus 1. From minus 3 to minus 1, portion is common here. So I'm looking for that portion of A which is not there in B. So that would be from here up to here. But I cannot take this minus 1 either because minus 1 is there in B. I'm looking for those elements of A which are not in B. So that would be minus 1 open, and then from minus 1 up to 1 is what we have here. So this is what A minus B is gonna be. In the A minus B, we have elements from minus 1 up to the point 1, excluding the endpoints here. Let's consider the second one, option B minus A. We'll think about B minus A this time. B minus A means I'm looking for elements inside B, but they should not be in A. So elements of B which are not in A. So let me use a different color here. I'm looking for elements of B which are not in A. So from here to here, everything which is there in B is not in A. So I can take the 3 or minus 3 also because minus 3 is not in A. So minus 3 is fine by us. Minus 3 is not in A. And then this portion, if I look at, it is there in A, so we'll not consider this one. As for the right side one, this is not there in A either. So this is also good. So this is what B minus A is going to be. The B minus A is from minus infinity to minus 3. Minus 3 is allowed. Union 3 to infinity. Which basically is same as from the whole real line R, from the whole of real line, I have erased this portion from here to here, which is minus 3 to 3. So from the real line, we are erasing the portion minus 3 to 3. Minus 3 open because I am taking minus 3. 3 here because I am taking 3 also. Had it been an open circle here, I would have put the closed bracket here. So that's the idea we have. So B minus A is set of all real numbers minus minus 3 to 3, which is not what is being told here. So this option is not correct. The question was which statement is not true? This statement seems to be false to us. So this is the answer we are looking for, option B. I'll do the C and D also. This time in the third option, we are looking for A intersection B. A intersection B means we are looking for the portion which is common between A and B. So this is the B we had earlier. Now common portion between A and B. So that seems to be the case from here up to here. That would be the common portion. So it's the minus 3 here. And minus 3 cannot be taken because minus 3 is not even there in A. So the common portion would be from minus 1 up to the point minus 3. Everything is fine. So A intersection B is going to be from minus 3 open here up to minus 1. Minus 1 is closed because minus 1 is common to both. So this statement is correct. In a similar manner, option D will check. We want the union this time. Union of A and B means we'll just club together the whole portion shaded one. So that would be, so A union B would be the whole of this thing plus the whole of this thing and then the whole of this thing. So let me just draw it separately. It would be 1 here, 1 is not to be taken, 3 here, so 3 was taken. So the union would be elements from 3 to infinity and then 1 to infinity, minus infinity to 1. So when we were talking about union, we were talking about collecting the elements of both of them. So I considered everything in B up to, and then this thing also we have to consider. So when you combine these two, it just extends up to this point. That's why I included the 1. 1 is not included because 1 is not there in A, and 1 is not there in B either. And then we started from here 3 to infinity. So this is what we have for A union B. And that would be same as, so what we have done is I can write it using intervals, but I'll try to match it with the option. The whole real line, from this whole real line, we are erasing this portion. So that would be from the whole of real line, I need to erase 3 is here taken. So that would be my shaded region does not have 1 in it which means from the whole real line I need to remove this one. That's why I'm putting the closed bracket here, and then my shaded portion does have 3 here, so will not remove the 3, so that's why the open interval 3. So this option D is also correct, though this statement is the only one which is incorrect here, and that gives us the answer we are looking for. It's option B here. Let's take a look at the next question now. It's slightly different this time. I've given two sets here. In the first set, I am talking about a set S. S is a set of all those points in the xy plane which are at a distance of 5 units from the origin. So let's talk about S first. S is the set of all the points in the plane which are at a distance of 5 units from the origin. Let me suppose the point is of the form P. Let's say A. Let AXY be the point. Suppose A is any point which is at a distance of 5 units from the origin. Which is at a distance of 5 units from the origin. Now the distance formula tells me OA is going to be equal to 5. I'm using the distance formula then. OA is 5, which implies OA square is gonna be 25, which tells me x minus 0 square plus y minus 0 square. I'm using the distance formula here. X minus 0 square plus y minus 0 square is equal to 25 on the right side, which is same as x square plus y square is equal to 25. Now let me mention an equation here. I'll just talk about the general equation of a circle first. General equation of a circle. We're talking about general equation of a circle here. Any equation which is of the form x minus h square, x minus h square plus y minus k square is equal to r square, that represents equation of a circle. It represents equation of a circle with its center at the point h comma k and radius at the point r. Radius is equal to r units. Center is at the point h comma k. Radius is r units. And this is what equation 1 represents here. In the equation 1, I have a circle which is having its center at the origin. Radius is 5 units. H is 0, K is 0, R is 5 units. So this is basically a circle for us. We have a circle centered at origin, radius is 5. So let me draw it here. I have the circle centered at origin, radius is 5 units. That's so question was I have a set of I have said I have the set of all those points in the plane which are at a distance of 5 units from the origin, and we just figured this actually represents the equation of a circle. Circle is centered at the origin in this case. H is 0 here, K is 0, radius is 5 units. So that's how we did this. We drew a circle. So in the set S, what we have is all the points which are lying on this circle. That's what the set S represents. Set S is the collection of all those points in the plane which lie on this circle. Now we'll talk about the set T then. For the set T, question says T is the set of all those points P in the xy plane such that P, Q, and R form the vertices of a right angled triangle, right angled at Q. So I have a right angled triangle. So we have a triangle right angled at Q. So we have a triangle PQR. Coordinates of P are x comma y. Coordinates of Q are 2 comma 3. Coordinates of R are 1 comma 2. Question says set T is the collection of all the points P in the plane which give me a right angle triangle right angled at Q. Now if this triangle is right angled, I can use Pythagoras theorem. Pythagoras theorem gives me hypotenuse squares PQ square PR square plus PR square would be equal to PQ square plus QR square. So let's see what happens when we use the Pythagoras theorem. PR is going to be x minus 2 square plus y minus 3 square. On the right side I will have PR x minus 1 y minus 2. PQ square would be x minus 2 square plus y minus 3 square, and for the QR square I will have x minus 1 square QR, so that would be 2 minus 1 square plus 3 minus 2 square. Now let's simplify this thing. We'll have x square plus y square minus 2x minus 4y plus a 5 on the right side, and then simplifying the right side of the equality, we'll have x square plus y square minus 4x minus 6y, and then 1 here and then another 1 here. So let's simplify this now. X square and y square on both sides, they cancel out. I'll shift the 4x on the left side, I will have a 2x. I'll shift the 6y on the left side, I will have a 2y. And then the 2 when shifted to the left gives me 3 here. So we are having this equation 2x plus 2y is equal to 2x plus 2y plus 3 is equal to 0. So we'll mark this equality, which represents a straight line. On the xy plane, we'll draw it. Let's just check our calculation once. PR would be x minus 1 square plus y minus 2 square. PQ square is x minus 2 square plus y minus 3 square. As for the QR, we have 2 minus 1 square plus 3 minus 2 square. Okay, we are missing out on these numbers. A 4 from here and the 9 from here. So this is what we are getting then. 2x plus 2y, and then that would be 15 here. Shifted to the left, I will have minus 10 is equal to 0. So this is the equation of straight line we'll be having. X plus y is equal to 5. Let me draw it on the xy plane now. When x is 0, y is 5, that point would be here. When y is 0, x is 5, that would be here. The straight line we are talking about is, let me use this ink. It's gonna be this line. So this black shade that we see here is representing the set S. The straight line in blue represents the set T. Except if we go back to the set T, question says T is a set of all those points in the plane P for which PQR form the vertices of a right angle triangle. I have this Q with me, I have this R with me, and I just got an equation. Coordinates of Q are 2, 3. Coordinates of R are 1, 2. If you see, if I put the coordinates of Q in this equation is satisfied, which means P and Q will coincide and there would be no triangle forming then. This equation represents the set of this equation is representing T. In the T we had taken points P of the form x, y, and we just got this equation. This equation is supposed to be satisfied. So in the set T, elements are of the form x, y and x plus y is equal to 5. Now we were choosing the point P in such a manner that PQR form vertices of a right angle triangle, which means I cannot take this Q here, because if I do take Q, P and Q coincide and there is no triangle forming then, which means I need to add a condition here. I cannot take xy is equal to 2, 3. So that point 2, 3, which is somewhere over here, I cannot take this point. So I'll just put a circle around it. So this is what is happening here. That's the only difference. Although I'm allowed to take anything for P, except I cannot take those coordinates of P, which will give me the Q itself, because I want the triangle to be, we want the triangle first, and it should be a right angle triangle. As soon as I take P is equal to Q, there is no triangle. So that's why I cannot take the point Q for the point P. So that's why we are not going to take the point 2, 3, and for which we are putting a circle around it. This is the point for 2, 3. Let's say this is 2, this is 3. So coming back to the first part of the question now, what is S intersection T? Does T represent a straight line? S intersection T, so these two are the points of intersection for the set we are at. So the S intersection T would be the 2 points, I'll just write their coordinates, 5, 0 and 0, 5. So we are not taking Q. We are not taking Q because PQR doesn't form a triangle when P coincides with Q. So that is what S intersection T is. Lastly, question was, does T represent a straight line? We just saw, although the whole thing is a straight line, but we have not taken one single point on this. So no, T is not gonna be a straight line. T does not represent a straight line. So to just, we'll go through it once again. S was given. S was the collection of all those points which were at a distance of 5 units from the origin. T was the collection of all those points in the plane for which PQR form a right angle triangle, right angled at Q. So We took any random point AXY in the set S, which is at a distance of 5 units from the origin. We used the distance formula. We observed some equation was coming, and that equation was equation of a circle centered at 0, 0. Radius was 5 units. So I drew the circle centered at 0, 0, radius 5. Then we talked about T. In the set T, collection of points is the collection of these P's for which PQR forms a right angle triangle. So right angled at Q. So we considered taking the Pythagoras theorem. Hypotenuse square was equal to base square plus perpendicular square. So that gave me this equation upon simplification, x plus y is equal to 5. So question says this P will satisfy this equation x plus y is equal to 5. But I was also observing the fact that Q that I see here 2 comma 3 also satisfies this equation, which means there is a possibility that P can coincide with the point Q. But I don't want the P to coincide with Q. And that's why when I wrote the T again, I mentioned I cannot take the point 2 comma 3. So I can take any point of the form Pxy that xy should satisfy those xy should satisfy x plus y is equal to 5, but they must not take this form 2 comma 3. So this is the form for the set T, which is this line, except this point has been removed now. So question was find the intersection of S and T. They are intersecting at this point and this point, coordinates of which are 5 comma 0 and 0 comma 5. And the other thing was, does T represent a straight line? Since we removed this point out of it, it is not going to represent a straight line. So I'll stop it here. Thank you, everyone.